Join us on an investigative journey as we educate each other on a scientific discovery, concept, or phenomenon.
Then we'll take a dive into the complicated and misleading world of pseudoscience to sort the factual from the fabricated.
I'm Matt McCabe.
And I'm Levi Bateman.
And this is Idiofacto.
It most certainly is. And this is summer.
It most certainly is that.
We, today, had our sort of first warm day.
You did.
I did, yeah. Well,
Up in New South Wales, we've been having much of the warm weather and many of the hot, smoky things.
Yes, yeah, you guys are very warm. Us in the sheltered southeast of South Australia, we're just experiencing our first day of 30 degrees. And no one knows what to do with themselves.
Oh, well, you know, I remember those days.
What of living in Mount Gambier?
No, of having 30 degrees, but that feels like it was years ago now.
Oh, what have you got now?
Well, tomorrow's going to be 42, so...
What? Oh, man.
Yeah.
I feel like hot days is one of those things that if we get a slow start to summer, everyone complains about it and whinges about the fact that it's still only 18 or 20 degrees. And then the first day that it gets over 40, everyone loses their minds.
Yeah, well, just for reference for our actually quite numerous American listeners, 40 degrees Celsius is 104 degrees Fahrenheit. So that's pretty hot.
Pretty warm, yeah. But it's not uncommon.
Not in Australia. I think in all of my time in America, I think it probably got over 100 maybe 3 times.
Right. Okay. I mean, I guess it depends what part of America or what part of the world you're referring to. As we've spoken about before, Death Valley is one of the hottest places in the world.
True, yeah. Well, I spent a lot of time in the northeastern states, actually working in a summer camp with Molly from Yeah No Yeah. And yeah, I think the hottest we got there was 102, and that didn't happen very often. So temperatures like this, I guess we can't attribute one lot of these temperatures to climate change, but, you know, something like 7 of the 10 hottest years on record have been in the last
decade. Yeah, that's right.
That's, I mean, that is a...
It's a fair old trend.
That is a trend that's worrying.
Mm-hmm. It most certainly is.
If you want any more information on that, go and check out our episode number 11, I believe it was, called Climate Change. And still, by far, the most popular episode to date.
Yeah, absolutely. Well, something a little bit different to climate change. This week, I'm going to be discussing... you've probably heard me say the word crisp before.
Yes, I have.
And those that know me well probably have almost definitely heard me say crisp.
I think one of the first times we met, I was very confused.
If you don't know me well enough to know that I say... Anyway, that's
It's got to be as ridiculous as you can possibly make it. It has to be drawn out, long, loud, really emphasize the part of it. Because, yeah, like that. Yeah. It's a very Levi thing.
Yeah, absolutely.
What has this got to do with science?
I suppose it doesn't really, but this week I'm talking about CRISPR.
Do you mean CRISPR or do you mean CRISPR?
Well, I suppose we could... I need to stop saying that word.
It's going to be hard in this topic.
So this week I'm talking about CRISPR, which stands for, and you can see why they call it CRISPR, because it stands for Clustered Regularly Interspaced Short Palindromic Repeats, which sounds a little bit confusing and a little bit like waffle, but it did.
Can I try and work out what that means?
Absolutely. Do you want me to say it again?
Yeah. So, clustered means that they're grouped together.
Mm-hmm.
Repeated?
Regularly interspaced.
So they're spaced at a regular interval, I would guess that would mean.
Good guess.
So groups of things that are spaced regularly.
Uh-huh. Short palindromic repeats.
So short, obviously, means short.
You're good at this game.
Palindromic means... it reads the same forwards as it does backwards. So like 212 is a palindromic number because it's 212, and backwards it's 212.
That's right. And a palindromic word is like Glenelg or the phrase, "Madam, I'm Adam."
Yes. Or race car.
Yeah,
It's
exactly.
the same forwards as it is backwards. So, and then repeats is the last one. Is that right?
Repeats, yep.
So I'm guessing it's a sequence of I know that it has to do with DNA, and that's about the only thing that I know about CRISPR. So I know that it has something to do with DNA. So I'm guessing that it's base pairs that are palindromes that are clustered together at a regular spacing. And that's about as far as I can get with that.
I mean, you're essentially right. That's exactly what it is. Basically, CRISPR is this natural process that's present in a lot of prokaryotic cells. I know we've spoken about prokaryotic versus eukaryotic cells before on the show.
Yep.
Prokaryotic cells are typically more basic, more ancient. The prokaryotic cells evolved first, and then eukaryotic cells evolved after that. But we don't really need to know too much about that. Basically, this CRISPR was a natural process in these prokaryotic cells, and it was originally used, and still is used, in these cells as an immune system against viral attacks in bacteria and archaea.
Right.
So inside the bacterial and archaea cells, there are these CRISPRs that are these short sections of DNA, they kind of just float around, that are taken from previously attacking viruses. So a virus will come in and attack the cell. That's sort of the way that viruses work. They inject their DNA into another cell, and then the DNA gets integrated and mucks up the coding of the cell, essentially.
Yeah.
That's kind of how viruses work. So these CRISPRs are these short pieces of DNA that are taken from viruses that have previously attacked the cell, and they're stored inside the bacteria. It's not the entire genome, it's just sort of a short segment of it.
Short, regularly spaced palindromic repeat of it.
It's pretty well, yeah. It
Right.
goes towards producing a CRISPR. So,
Right.
like I've said,
Okay.
it's not the entire genome. It's just a small enough section that you would recognize it if that virus were to come in again. So the bacteria still has its own DNA. The CRISPR region is separate. So now that these short sections of virus DNA are stored in the cell, RNA can be produced that matches the DNA. So just for a quick reference, DNA stands for deoxyribonucleic acid, and RNA stands for ribonucleic acid. So RNA is essentially, chemically it's pretty similar to DNA, but its structure, it's like it's only one half of the DNA. So if you imagine that the DNA is like a twisted ladder, RNA is only one half of the ladder, and it's usually only in short segments. It's used for coding, for transporting code around the cell.
Because that's the handy thing about DNA and RNA is that because it's a code, the base pairs only match with one other type of base pair. If you have one strand of it, then you've basically got the whole code.
Exactly, yeah, because it can only match with its opposing pair.
Yeah.
Yeah, so now that the cell has made this RNA, the RNA from this that matches up to this little CRISPR, this RNA gets attached to what's called a Cas9 protein, and Cas9 stands for CRISPR-associated protein number 9. So it's just a protein. There's lots of different types of Cas proteins, depending on what the organism is that we're getting the protein from. But essentially, they're all involved in the CRISPR process. So science observed the use of the Cas9 protein in a bacteria called Streptococcus pyogenes.
There's another pronunciation of a species name. But you did that one quite well, actually.
That was perfect, yeah. I'm going to start judging you on all of your pronunciations from now on.
You're very welcome.
So the Streptococcus relies on this Cas9 to carry out this CRISPR function. So the RNA gets attached to this Cas9 protein, and then it kind of just floats around the cell. And the RNA is like a little tail, and the Cas9 protein is like a big blob. So it just sort of cruises around the cell. The function of the Cas9 protein is to act like a pair of molecular scissors that is specifically designed to only snip DNA. So as this thing floats around the cell that's made up of a Cas9 protein and a little tail of RNA that's specifically previously coded to a virus, if a virus attaches itself to the cell and injects its DNA into the cell, the RNA on this Cas9 protein will recognize the virus's DNA. Because essentially, as we said, this RNA is half of the full DNA. So it will float around and it will match up. So this section of RNA will directly match up to a piece of the virus's DNA. It will recognize it. And then the Cas9 protein will attach to this DNA strand at that section, and it will snip it in half. And it will essentially render that clump of DNA useless.
And so the most interesting thing about these processes are that it's not like a conscious process. None of these proteins or molecules, so DNA, RNA, Cas9 proteins, none of them recognize consciously what they're doing. It's a chemical process. It's what would happen in a petri dish if you just put these chemicals together.
Exactly right.
But the function that it performs is so helpful to the organism that that's how it's evolved these proteins.
The bacteria isn't actively thinking, oh, I've just been injected with a virus, time to whip out my Cas9 with the carrier RNA and, snip this virus's DNA in half. It's not a process that's actually, the bacteria is not cognizant of it. Like you say, it's just happening. It's a chemical reaction. Like if you were to add vinegar to bicarb soda, you're going to get a reaction. In the same way, this is a reaction. The protein is a chemical that perfectly reacts with a piece of DNA, with a chemical called DNA.
And the thing is, though, when we're talking about things like this, it seems so purposeful that it's hard not to give these proteins agency. Do you know what I mean? It's hard not to imagine that they are thinking about these things, these actions, because it seems so directed and purposeful.
Exactly. And it probably doesn't help that I've said words like recognize. I said that the Cas9 protein would recognize the virus's RNA. Well, it's not really recognizing it.
That's how biologists refer to these things, though. It's not you.
They do, yeah, exactly. But it does make it seem like...
It gives it agency that it doesn't have.
Exactly. Yeah, at the end of the day, it's just a chemical. So this process, this CRISPR-Cas9 process, is the cell's defense system against virus attacks. And if you want to see this process in action, there are some really cool animations. And if you want to hear a catchy song, and it's a parody of Mr. Sandman, I'll put the links in the show notes to a parody song called CRISPR-Cas9, Bring Me a Gene. So it's pretty clever, and it's got some great animations in it that show you how this CRISPR system works. I also found a really great GIF that actually shows a real microscopic image of this Cas9 protein working on a strand of DNA. Do you want to see it? I'll send it to you now.
Yeah, do.
So can you see the blob that's Cas9 RNA?
Yeah.
Sort of snipping, it attaches to this strand that is DNA. And it sort of just wiggles around.
Yeah, and cuts it in half.
It would slightly denature, and then one end of the DNA that's in it just kind of floats away.
Yeah, that's so interesting.
Yeah, so that's how this process works. It's actually incredible that this all evolved inside of a bacteria. So this process was discovered independently in 3 different parts of the world throughout the sort of late 20th century, throughout the late 80s and 90s, and then into the early 21st century. And then in March 2007, it was discovered that the CRISPR system is an adaptive system. I believe it was in a dairy where they were testing against viral attacks on a certain type of bacteria that you use to make yogurt and cheese. And this bacteria was getting attacked by virus. And so they did all these experiments in this system on behalf of the dairy. Basically, they introduced a new virus to this bacteria, and the bacteria could produce new CRISPRs and defend against new viruses that it had never come up against before.
So it's like it really is like an immune system.
It's exactly an immune system, because I guess the only thing that really, or the only biological living thing that can attack a bacteria is possibly other bacteria or viruses. So they don't need to have a super complex immune system. I mean, this is complex, but they don't need to have an immune system like ours.
Yeah, it's not quite as complex as ours is.
No, that's right. So, like with lots of new discoveries, there wasn't really a great deal that was known about it at the time. They knew that it worked, and they sort of knew how that it worked, the scientists that discovered it, but there were no real proposed uses for it. It was just a massive breakthrough and a discovery at the time. They didn't know how to use the system until this scientist Feng Zhang and his team successfully harnessed CRISPR-Cas9 for genome editing. And you remember how gene editing and genetic modification works from our episode last week. So we can actually, this is incredible, I think, we can use this naturally occurring process that evolved inside bacteria to edit a creature's or an organism's genome. So the way that this process works is by cutting DNA at a given point in the genome at a gene that you're targeting. And then you can edit that gene or replace it with a different type of DNA. So usually when DNA gets cut inside a cell, the cell has a few different ways of repairing the DNA, and often it's not great, and sometimes it can result in mutations. And this is why any process that damages DNA is not great and can lead to tumours and cancerous growths and this kind of thing. These mutations occur. But under a lab-controlled situation, we can actually give the cells the DNA that we would like to repair itself with.
So it's like a natural version of the gene gun that you were talking about last week.
Sort of, but it's far more controlled. So the gene gun is just randomly blasting genes inside the nucleus of a cell,
hoping that they stick,
in the hope that it will get taken up.
This is a targeted and clinical sort of...
Yeah, very much so. It's true sort of gene engineering on a microscopic level. So, for example, this P53 gene, which is essentially a tumour suppressant gene, they often call it the tumour protein gene. And if there's a mutation in this gene, then this tumour suppression system doesn't work, and mutations occur. And this is what leads to a lot of different types of cancers, is this P53 gene inside humans. But what we could do is we could use CRISPR to cut out that mutation and then let the cell repair itself and repair the DNA where this gene's normally found with the appropriate gene that doesn't have a mutation in it. So if we can do it with this, we can essentially do it with any disease, any illness that is genetic in nature.
Yeah, that's amazing.
The possibilities are seriously almost endless. Currently, we aren't really using it much on humans.
Well, I guess the ethical problems alone would be...
Exactly. Yeah, I'm about to get into that. And the ethics are super interesting. We are kind of using it a little bit on humans at the moment, but so far it's just used as an incredibly useful genome editing tool for GMOs. But seriously, imagine if we could use this technology on humans.
So it is currently used to genetically modify organisms?
Yeah, for sure.
Just not humans?
Not humans, no.
So we understand it well enough to successfully modify the genes of other organisms?
That's right, but we've been modifying genes in organisms for some time, or non-human organisms, I'll put it that way. I think the thing about CRISPR is that we could use this for diseases, and you could use CRISPR on an embryo that we know has a certain genetic mutation, and you could insert the correct gene. And like I said, theoretically, this could be used to treat any disease that has a genetic cause. And not all diseases are caused by genetic mutation, but a lot are.
It's funny when you say, like, the correct gene is, like, I'm thinking at it from a philosophical point of view, I'm thinking, well, what is the correct gene?
Yeah, you're right. Yeah. And
I know what you mean in that context. Like, the correct gene is one that's not defective, but then... I guess from an ethical point of view, people have different views of what the correct gene may be.
Well, yeah, you're bang on. And this is the thing, is that we sort of can't really test it on humans because it probably would be unethical to test it on an embryo, I suppose, because the argument is that the embryo can't give consent, if you know what I mean, and we're editing its genome, so you're changing it at a genetic level from the way that it would have been born to the way that we think is right. I think it probably is appropriate, and for diseases... I don't really think consent should come into play because there's all sorts of diseases that we treat unborn babies for, and they don't give consent. And if somebody has an accident and they can't give consent, we'll still give them treatment to save their life. So for me, this isn't really all that much of an ethical issue, but we are still playing with a human's genome, and I guess there are all sorts of ethical arguments about this. When does a human become a human?
Exactly. And the thing is, like, people say, oh, it's a slippery slope. Like, if you start editing out the genetic defects, meaning diseases in embryos, then people might say, well, while you're in there doing that, you might as well cut out the brown hair and put in some blonde. But that's a slippery slope argument, and it's not. It's a logical fallacy. A slippery slope argument is a logical fallacy because we regulate these things constantly. In nearly every aspect, there's a grey area. There's never a black and white. It's always a continuum. And given strict and well-researched regulation, it shouldn't become too much of an issue.
Exactly. Well, it shouldn't, and it just about can't in the way that you're referring to. So I think, like you've said, people are sort of worried that CRISPR might get used to change people's appearance. Like you could change your child's eye colour, or you could change your height to make sure you're a certain height, or change your facial structure, so on and so forth. And technically, we could change all of these things with CRISPR, but the thing is we don't actually know how yet. So we know how to change I call it a simple gene, but we know how to modify a gene that we know exactly the code of that gene. For example, the P53 gene, we know what it looks like and what it should look like when it's working.
Yeah.
But we don't really know what genes code for our phenotypes. And it's sort of not as simple as that. It's believed that it's far more complex than, for example, one gene for eye colour and one gene for hair colour. So even if people did want to change the way that their future children or offspring are built or put together, we don't really know how. Yet. Yeah, that's right. So I think so far, at least in the testing phase, its best use and its most appropriate use would be for disease control, genetic disease control.
Yeah, but even then, I think any regulation should be future-proof as far as possible. So it would be pertinent to add in regulations that deal with the ability to make whatever you want to call them, aesthetic modifications or non-pathological modifications, if you know what I mean.
But I suppose, there's all sorts of processes that we could do to children, but many of these are illegal. Like, it's illegal to give a child a face tattoo. You know what I mean? In most of the Western world. Yeah. And there are laws that protect against it. So why would this be?
Yeah, and that's my point, is that there's always the capacity to do serious damage, or be unethical about various things. And that doesn't mean that we should avoid the issue altogether.
Yeah.
Like, we haven't banned tattoos for all humans because potentially maybe they would give a child a tattoo one day. There are regulations against that. So we're not avoiding the process altogether just because it could be potentially used for ill purposes.
Yeah, exactly right. There are ways to regulate any process. And just because it has the potential to do some sort of crazy things doesn't mean that it's going to be allowed.
And that shows the importance of research and knowledge and having these sorts of discussions.
Yeah, and appropriate controls too. I think CRISPR is fantastic. Like, another use for it is potentially to play around with the genome. And I say play around sort of in inverted commas because it's a pretty complex thing to play around with. But what we really could do is we could make changes to a certain genome and see how this changes the phenotypical expression. So, for example, we might theorize that a certain gene within a certain chromosome is responsible for a certain trait in a human, but we're not sure, we're not 100% sure. So we might use CRISPR to modify that gene, and then we could observe what the change is in the individual. It's probably pretty difficult to do this in an adult, but you could do it in the laboratory. You could do it in a test tube, in a petri dish, if you know what I mean.
Yeah.
But we actually are using it on adult humans. In July 2019, a 34-year-old patient in the US was treated for their sickle cell anemia. This CRISPR-Cas9 was injected into the body, and it's gone to work to find the faulty gene in all of the patient's cells and to cut it and to replace it with a gene that's useful, that doesn't produce these sickle cells in the blood.
Has it worked?
Well, this is the thing, is that it only happened mid this year, and all the doctors that performed the procedure were very hopeful that it could cure the disease, but because it's so new and because it's such a long process, it could take months or years before we actually know if the treatment was first effective and secondly safe.
Yeah.
So as we know with anything that's genetic, there can be mutations along the way. So if some of that RNA were to somehow replicate or to mutate along the way, it may target a different gene. So it's still very experimental. But what this basically means is that we can use CRISPR on adults as well. There's huge applications in both medicine and potentially in cosmetic procedures.
Ugh, that makes me really uncomfortable, but yeah, sure.
That's right, yeah. And this is one of the worries, I guess, is that if we get it to the point where you can inject this CRISPR-Cas9 into your body and it can go to work giving you a smaller nose or different colour skin or something like that. But if we did work out how to do that, it probably wouldn't be the worst thing. Loads of people get cosmetic surgery. And if I wanted to, I could go out and get cosmetic surgery, but Just because it's available doesn't mean that I'm going to do it, if you know what I mean.
Yeah, that's true. And at the end of the day, they're consenting adults. It's hard
Exactly
to...
right. Yeah. Yeah, if we're not doing this to embryos or to children.
To a point, obviously. Again, it's all about how it's regulated.
Yeah, that's right. And for a while, it would be a fairly risky procedure, but so far, it's the most hopeful and reliable way to edit the human genome and correct for mutated genes. So I suppose just to wrap it all up, basically this CRISPR-Cas9, it's very, very new. Like I say, it was only discovered essentially in the last decade. There's loads of red tape that we need to get through. As with anything, human testing is always going to be difficult, especially when it comes to genetics, and it's seriously fraught with ethical issues. But I think, watch this space, because I wouldn't mind betting that CRISPR will be a household name within the next 50 years.
So have you read or seen The Hitchhiker's Guide to the Galaxy?
I can't read.
Oh, well, have you watched the movie? This is why you watch videos all the time for your research, because you can't actually read.
Blew my cover.
1300624506.
That's the reading writing hotline. And everyone in Australia, everyone that grew up in Australia is singing along right now.
Yeah. Sorry, it's going to be stuck in your head for the rest of the day.
I have not. I've not read or watched The Hitchhiker's Guide to the Galaxy.
Wow. Okay, well, you really should.
Oh, I should.
Do you know what the answer to life, the universe, and everything is?
I do. I know enough about it to know that that 42 is the meaning of life.
42. Yeah. So in the book, the supercomputer called Deep Thought calculates the answer to life, the universe, and everything, and it's 42. However, it doesn't give any indication of what the question was, which pretty much renders the answer completely meaningless. Despite this being a completely fictional novel, some people, however serious they were about it, devoted way too much time and effort to figuring out what the question might be, with explanations ranging from binary representations of certain phrases to Tibetan monastic prophecies. But incidentally, in the sequel novel, The Restaurant at the End of the Universe, they actually did find the question, and it was, what do you get when you multiply 6 by 9? Now, to us modern humans, that doesn't make a whole lot of sense, because in base 10, 6 times 9 is 54, not 42. But in base 13, it's actually 42.
What? How?
Yes, solved.
What's base 13?
Well, you count up to 13 before you switch over to the next number.
Yeah, but 6 lots of 9 is still going to be 54, is it not?
No, because you'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you'd have like, I don't know, 11-1, 11-2, 11-3, and then you'd go back to, you'd write it 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you'd have a different symbol for 10, you'd have a different symbol altogether for 11, you'd have a different symbol altogether for 12, you'd have a different symbol altogether for 13, and then once you get to 14, you would switch and you would have the symbol for 1 and then the symbol for 1. So you would, 11, the number 11 would be the 14th number in the sequence.
Yeah, no, I got that part of it.
Yeah.
Yeah, no, I understood that part of it. It's going to take longer to get to the number 42.
Yes.
Yeah, right. Okay.
Yes, it's going to take longer. In fact, it's 6 times 9 would be 42.
Yeah, right.
Anyway, all of that is completely irrelevant because the point here is made obvious by the absurdity of the whole situation. Numbers are almost completely arbitrary.
Yeah.
As are dates, years, time in general. Like, for example, we're told that the length of a year is 365 days, or to be more specific, it's 365.25 days using the Gregorian calendar because we have a leap year of 366 days once every 4 years. But even this changes by a number of seconds year by year based on various astronomical factors. And a number of seconds doesn't seem like a significant amount of time in the scheme of things, but it could prove to be if you're a numerologist.
Ooh.
So numerology is, well, you tell me. Use your etymology skills. Numerology.
I'm going to go ology, meaning the study of, and numero, meaning numbers.
Yep. Numerous, which is Latin for number, and ology from the Greek for study, the study of numbers, numerology.
Right.
Once again, combining the Latin and Greek, which is cardinal sin, but,
Ideo
facto.
Yeah.
So a numerologist claims to be able to predict very specific details about your personality and destiny based entirely on the numbers inherent to your world. So your birth date, the year you were born, the number of siblings you have, but most commonly your name number, which... Go on.
No, it was just a sigh of frustration.
Yeah.
This is already starting to sound a lot like astrology.
Well, interesting that you say that. Your name number is a special number, and it's based on the letters of your name, and it reveals the subject's outer nature or the personality that you exhibit to the world, basically.
Okay.
The name number method was actually developed, at least in part, by Pythagoras, who, despite figuring out the relationship between the length of sides of a triangle, quite obviously lived in a pre-scientific time. He also discovered that musical scales were based on actual mathematical ratios in the frequencies, but all without understanding what a frequency was. But that's a story for another day.
And that is actually amazing, the fact that musical notes are based on mathematics and are almost pre-programmed in our heads. And I'll give the link to this video, I'll put it in the show notes. Have you seen the video of Bobby McFerrin jumping around the stage, and each place that he jumps is a different note? And he sings along for a short amount of time. He sings along, and then he gets the crowd to sing on the same note, and then he jumps but doesn't sing, and all of the crowd hits exactly the same note.
Really?
Because it's a given interval, and everyone understands what's called the pentatonic scale without him prompting it. Everyone sings exactly the same note.
That is actually amazing.
It's amazing. I'll link it in the show notes, and you should all watch it. But you're right. Sorry, that was a digression, but it just goes to prove that music is sort of inherent in our brains, and it's mathematical. Yeah.
And so the Pythagoreans were the first to actually understand that music is mathematical.
Wait, Pythagoreans?
Yeah.
They were a group of people?
Yeah. I mean, it's hard. When you go that far back in history, it's hard to establish whether it was one person or a group of people who were doing this work. Historians just refer to the research that came out of that part of the world at that particular time as the Pythagoreans.
Well, that is a fantastic name for both a band.
Yes, that is a good name for a band. Now we've shared it with everybody.
And a quiz team.
Oh, yeah, that is good too.
The Pythagoreans. I like it.
Anyway, the fact that Pythagoras or the Pythagoreans were involved in what's now considered to be legitimate science and also more mystical science, or as we refer to it these days, pseudoscience. Mm-hmm. Many numerologists use this as a pseudoscientific explanation of, they use Pythagoras' involvement as vindication of the method, and they say that the way that numbers influence the vibrations in the fabric of the universe, and uses phrases like that, which, of course, that's not supported by any science ever. But they use it as a way to legitimize their practices.
I mean, I'm sure there are vibrations in the frequency of the universe or something, but it's certainly not resonating with whole numbers, and certainly not with numbers that are attached to your name. Exactly.
And so what's interesting about those ratios is Pythagoras sort of shrunk them down to easy whole integer ratios. But in reality, if you look at the proper frequencies, the ratios are much more complicated than just 1 to 2 and, 1 to 4 and that sort of ratio. It's a lot more. It's like 10,005 to 25,104 and things like that. So like the ratios are not as simple as, for all intents and purposes, for all practical purposes, they are very simple. But when you actually look at the science behind it, it's a much more complicated. Obviously, it's always much more complicated than it seems. Yeah, the universe is messy.
It is, yeah.
Anyway, Pythagoras was obsessed by interesting numbers, and he did find quite a few interesting numbers, and some numbers are particularly more interesting than others. In fact, there's an entire YouTube channel called Numberphile, which is almost entirely about interesting numbers. And I would encourage you to check it out. I'll put a link in the show notes. Really interesting YouTube channel, all about numbers. So if you're a massive nerd like I am, then go and check that out. Even if you're not, you might find it entertaining.
I have seen some of these videos and they are very entertaining.
Yeah. In any case, numerologists took some of these Pythagorean numbers and somewhat arbitrarily assigned them personality characteristics.
Right.
Going back to your name number, you can work it out by adding the numbers that are assigned to the letters in your name. Again, they're arbitrarily assigned to your letters. And then you add all of those numbers together until you get a number between 1 and 9.
What?
Or 11.
What?
Or 22, because 11 and 22 are special numbers for some reason.
Wait, what do you mean you add them together until you get between 1
Well,
and 9?
I'll show. Let's try it for you, and I'll see what you. So spell your name, and I'll tell you what number the letter that you spelled to me corresponds to, and then write it down. Have you got a pen and paper?
Sure. My name is Loodle Voodle. My name is Levi. L.
Yeah, that's worth 3.
E.
Is worth 5.
V.
Is worth 4.
I.
Is worth 9. So you would write down 3 plus 5 plus 4 plus 9, and then you'd add them together. So Levi equals 21. Mm-hmm. So to save you the trouble, the rest of your name adds up to 85. I did that for you.
Great, thank you.
Yeah. So Levi Stanley John Bateman adds to 85.
Right.
Yes, okay. I used. So that's you use your whole given name. And then, so the 8, you've got the 85, then you add the 8 to the 5, which gives you 13. And then that's not one of the special numbers, and it's not a number between 1 and 9. So then you add the 1 to the 3, which gives you a 4. So you're a personality type number 4.
What?
Do you want to know what that means?
Well, I could probably tell you what my personality is. I'm
going to tell you what your personality is.
Yeah, you tell me.
Because I know, because I've done
your name number.
Yeah. You're stable, rigid, sure-footed, determined to reach your goals in a straight line. When things come without effort, you're uneasy, wondering if something is good if it comes without hard work. Often you're so focused on your goals that you miss the small pleasures in life. You are stable, security-loving, and often unmoving and dull.
Right.
So I think that's pretty accurate, really, for you.
Do you? Yeah,
especially the unmoving and dull part.
So speaking of not enjoying the small things in life, the other day I was walking into town with Christy and we passed a property that had about 6 different types of roses out the front, and we stopped and literally smelt the roses, every single type of rose, to see which smelt the nicest.
Well, 4's biggest challenge is to find the middle of the road so they can have balance in their lives. So maybe that smelling of the roses was actually to balance out the chaos that was the rest of your life.
I suppose.
See, I could be a numerologist.
Yeah, I suppose.
So I actually added up the numbers in my name as well, and I came to 11, which is a special number.
Oh, so
which
special.
Means I have special characteristics, because I have some characteristics of a 2, because 1 plus 1 equals 2.
Oh.
Right? And then I have some characteristics of 1s, because I have 2 1s in the number 11.
Right.
And then there are some other characteristics that are unique to 11s. So I'm like super special because I'm an 11. I'm not going to go into what the 11 actually means, because as we will find out, it's completely irrelevant. Do these readings sound like anything else we've encountered before? You alluded to it just before.
Yeah, it sounds exactly like astrology.
It's an astrological reading, basically, a horoscope. So like astrology, the personality predictions given by numerologists are vague and generalized, which takes advantage of the Barnum effect, which you talked about in relation to cold reading and tarot cards.
Mm-hmm.
Basically, it's the natural tendency for people to assign detail and specific meaning to generalized statements or events. It's a well-studied phenomenon, and there are some links in the description that talk about the psychology of the Barnum effect, but if you want a little bit more of an explanation, head back on over to our episode on tarot cards earlier this season, and Levi does a pretty good job of explaining it.
Thank you.
Also, like astrology, numerology relies on the facade of being particularly complicated and intricate to add gravitas to their predictions, using numbers and formulae to make it seem more sciencey.
Exactly. We've talked about this before, and it's almost similar to the placebo effect, in that the more extreme the procedure, the more likely you are to believe that it's affecting you or healing you.
A very similar psychological phenomenon, I would suggest.
And so the more complex this belief and the more set of rules that it involves, the more likely it might seem to somebody that hasn't overly analysed it, like us skeptics, that it might be a legitimate practice. You know what I mean?
Yeah, that's it.
It gives the illusion that somebody has studied it and has perfected it and, has it really nuanced out.
Yeah, exactly. But what are the chances that that humans have been able to stumble upon this way of predicting personality traits when we have no, keep an eye out for this topic in an upcoming episode. We have no agreed way of deciding personality types from a psychological perspective. So how does this relatively arbitrary way of deciding personalities actually hold up? So, I mean, unlike astrology, the proof that numerology is utter nonsense goes back to what I was talking about before, and that is that numbers are arbitrary. So, whereas astrology is a little harder to disprove, only a very slight bit harder to disprove.
Right, because I guess stars have always been around, haven't they?
Yeah, and the concept that stars and moons can have an impact on your personality is abstract and unbelievable, but the fact that numbers, which are human assigned and completely arbitrary, could have any effect at all is even less believable.
Well, so are names as well.
Exactly. So the only way numerology works is by assigning a supernatural value to what is an arbitrary human construct anyway.
Yeah.
A numerologist would, hand on heart, swear that if my parents had decided to name me Matthew with one T instead of Matthew with two T's, that then my name number, and I worked this out, would actually be 9, not 11. And that would mean I would have a completely different set of personality characteristics, just because my parents had decided to name me with one T instead of two.
What about people that change their names?
Well, then you change your personality. That's
They
honestly believe that the way that you can change your personality is to change your name.
Okay.
Yeah. Yeah. But it's also patently absurd and utterly illogical. The thing is, like, numerologists would have an answer to that, and they say that, you know, your name number is not the sole decider of your personality type because you have to take into account your birth date as well.
Oh.
But, I mean, that's completely arbitrary as well because we've assigned those numbers, and, like, if we had used a different calendar, then maybe we wouldn't have the same numbers go by the Chinese calendar, for example.
Exactly.
Does that change your personality?
And we have changed our calendar.
We have several times in the past. And also, like I said earlier, the difference of a second here and there doesn't make much difference in the scheme of things. But then if you are born at 12:01 on the 1st of January, then your birth year is determined by the number of seconds that it took. Do you know what I mean? Like, you could have been born at 11:59 on the 31st of December, 1989.
Yeah.
Or you could have been born at 12:01 on the 1st of January, 1990. And that could determine what your personality would be. And when you put it that way, that's ridiculous.
That's right. Well, as ridiculous as the difference in a day changing your star sign and therefore all of your horoscopes.
Yeah. Exactly.
There are so many similarities.
There are. I mean, it basically is a form of astrology.
Right.
But we've always fallen into the trap as a species of assigning meaning and patterns to random and unrelated things. And that's a psychological phenomenon known as apophenia. Have you heard of that before?
I think I have. Is this where can you train an AI computer in apophenia to find faces?
Yes,
in images where there aren't faces? I've seen some of these.
And so there's a few different types of apophenia. The one that you're referring to there is pareidolia.
Yes, that's it.
But apophenia is the general term that's applied to the phenomenon of seeing patterns where there are no patterns. And it's pervasive in humankind. And nowhere is it more obvious than when we go back to my original example of people trying to assign meaning to Douglas Adams' choice of the number 42 as the meaning of life, the universe, and everything. Adams himself gave an answer to that exact question, which is an excellent demonstration of how humans get a little bit silly about their apophenia, and it shows why numerology is just another example of people trying to assign meaning to chaos. He said, "The answer to this is very simple. It was a joke. It had to be a number, an ordinary, smallish number, and I chose that one. Binary representations, base 13, Tibetan monks, all complete nonsense. I sat at my desk, stared into the garden and thought, 42 will do. I typed it out. End of story." That's it for this episode of Ideo Facto. Forward all suggestions, hate mail, evidence and arguments to idiofacto@gmail.com.
And you can reach us on Facebook, Instagram, Twitter, and all other social platforms at Ideo Facto. Links are in the show notes. The Pythagoreans. I like it.
That's the name of our band. Nobody take it.
Yeah.
It's probably somebody already has, I'm sure.
More than likely. And they'll play excellent like math rock or something.
I'm going to look it up. You know, it might not be.
Did you type the Pythagoreans band?
Pythagorean band, yeah. I don't think it is.
Whoa.
It's ours now.
Let's not release this episode until we've recorded a few albums, got a record label, and have established ourselves in the math rock world.
I mean, we will well and truly establish ourselves as massive nerds if we called ourselves the Pythagoreans. But anyway,